Hi, welcome to this session on keeping games resilient and responsive to user demand. I'm Peter Chapman, and I'm a specialist solutions architect for gaming. In this session, we're going to look at some of the levels of resilience that are available with AWS services, and we'll explore ways that they can be used to make our games as available as possible for players. Let's start by looking at what we'll cover today. First, we'll spend a few minutes looking at why resiliency is important to games and why it matters for players. Next, we'll explore the different levels of resilience that we can make use of with AWS and how each of them work at a high level. And finally, we'll pull all of this together and dive into an example use case for a game, where we'll break it up into the main responsibilities and look at how we can make parts of our game highly resilient. So why is it important to make our games resilient to failure and responsive to demand? Many games today have a global audience that forms strong communities, and players are increasingly becoming time poor, so it can be frustrating if they're not able to get access to a game when they have time to play and jump in and enjoy some free time. If that happens frequently, it can quickly generate undesirable sentiment for the game itself, causing reputational damage over time. But the simple reality with games is that if your game does go down, then your players are unhappy. A large part of my job is working with studios around the world to help them design infrastructure that develops great gaming experiences for their players with AWS, including how to make their infrastructure resilient. So before we start looking at the individual levels, I wanted to share this thought with you. Component redundancy increases availability significantly. Through all of the options for resiliency that we'll look at, they all have something in common. They're using component redundancy to increase the availability of our game. By having more than one component that can act as a backup or is already being used to serve players, and if we lose one of those components, we're able to use the other to continue meeting demand. To start looking at the levels of resilience, we should first look at how AWS regions are structured at a high level. There are 19 AWS regions around the world today, with a further 4 coming soon. And each AWS region provides multiple physically separated and isolated availability zones, which are connected with low latency, high throughput, and highly redundant networking. Making use of multiple availability zones allows you to design your game in a way that makes it more highly available, fault-tolerant, and scalable than traditional single data center or multi-data center infrastructures. So it's a good practice to ensure that your game services and game servers make use of as many availability zones as possible within a region to ensure that they're as resilient as possible to failures. Also within AWS, we have services that automatically make use of all availability zones within a region, and that provides you with regional resiliency out of the box. In most cases, there is no need to specify that these services run in multiple AZs. They will do so as standard and will continue operating in the event of a failure at the AZ level. Here are some of the regional services that are relevant to game developers in AWS. They're useful in many different use cases, from object storage with Amazon S3 through to providing serverless HTTP service endpoints with Amazon API Gateway and AWS Lambda. We also have game-specific services within AWS. For running dedicated game servers, for session-based multiplayer games, we have Amazon GameLift. GameLift helps you to globally deploy your game servers and automatically scales them based on player demand. At this point, we have looked at resilience within one region. But what if we need our game to be resilient to failures that happen at the multi-regional level? By making a game multi-region, we get the benefit of reducing latency for players. This is, of course, a good thing for game servers, as there is often a need for a low latency link between the client and server. But it can also be good to help with other use cases such as data retrieval or updates from the game client to your back end. Having a low latency communication here can improve performance on the client side too. Crucially, running our game in multiple regions allows us to fail over in the unlikely event of an issue that affects us at the regional level. In this example, we have 2 groups of players, one group in Western Europe and another in Central Europe. Having a multi-region setup allows us to serve both groups locally from a region close to them. However, if we experience an issue causing us to no longer be available to communicate with the local services, as is shown here, with our players in London, we can fail those players over to the same region as the players in Frankfurt. We need to ensure that our services can scale to meet the new demand and that we can access the data to serve the London players in the failover region. So now that we've explored resiliency at the regional level and multi-regional levels, let's apply this to an example game type and see how we can use AWS to make it highly available. Here we have an example of a third-person battle royale game. It can support up to 100 players in the same game session, and sessions run between 10 to 30 minutes on average. From this, we can pick out some key requirements that this game type has. First, it needs to be able to store, update, and process player data. There will be a need to match players based on player properties such as skill, role, and other characteristics. Finally, we will need to distribute game content updates and patches to all clients. So let's break that down into a set of distinct responsibilities. We can group our need for matchmaking and player data interaction into back-end functions. We could compose these as services on our back-end to support the two tasks. Secondly, we need to be able to run our game servers in a resilient way, so we can look at this along with the need to discover what sessions are available and in which locations. And we have a need for a content distribution mechanism to allow the game clients to quickly and reliably download game content and updates. So starting with our back-end functions, we need to consider what our resilience needs are. For both matchmaking and player data access, these are part of the critical path of players getting into a game session, so we will likely want to make sure that we have a multi-regional redundancy in place for these. We can make use of several AWS services for back-end functions such as these. To provide the service endpoint, we can use Amazon API Gateway, which is a fully managed service that makes it easy to create, publish, maintain highly scalable APIs. We can trigger Lambda functions to execute the custom logic for our service. AWS Lambda is our compute service, which lets you run code without provisioning or managing any servers. For data storage, we can use Amazon Dynamodb, which is a fully managed NoSQL database. All of these services are automatically resilient at the regional level, without us having to configure or set anything up for that. To give us multi-region resiliency, we're going to use Amazon Route 53. Amazon Route 53 is our highly scalable and available domain name service. In our case, we will use it to route player requests to our back-end services for matchmaking and player data. It can use several approaches to routing that we can make use of to build high availability into our design. For our game, we could benefit from the player data service having a low latency response time for requests. We can use latency-based routing in Route 53 to route end users to an AWS region that provides the lowest possible latency. However, if we want to route players to a specific region based on geolocation, we can use GeoDNS to point them at a particular endpoint that you specify based on their geographic location. So in this case, we can see that a player located in the UK, Route 53 will detect this and route the players to the closest possible region, in this case in the EU. You can also specify the frequency or weights with different DNS responses are returned to end users with a weighted round robin. This is useful for deploying changes to your backend and testing them out on a small subset of players before rolling out to everyone. If there is something unexpected happening with the new version, you can quickly roll back to the existing one to fix any issues. Finally, you can also route your players to an alternative location to avoid outages using DNS failover. You can set a health check that Route 53 can use to ensure that your resources are available, and in that event, it will route them over to the other resource that's the backup. Returning to our backend service pattern, let's now focus on the database. One of the harder parts of running a multi-region architecture is having to multi-master our database in 2 or more locations. This will be needed if we wish to read and write locally to a database and also allow failover from other areas if we experience issues. as we are using Amazon DynamoDB for our data store, we can enable global tables to help us solve this challenge. Amazon DynamoDB Global Tables allows us to have multi-master databases in several different geographical regions. This allows us to globally distribute our game backend and run services in multiple locations. By doing so, we will improve the latency of reads and writes for our players accessing our game from around the world. In the unlikely event that we have a regional level failure occur, we are able to fail over to another one, knowing that the data we need is accessible from that region. And it's easy to set up without needing us to write any specific code to enable this. In the previous session, we talked about how to choose the right game server based on your game's needs. For our use case, we need a dedicated server to run a game session. Based on this, we're going to use Amazon GameLift to do so. Amazon GameLift automatically starts and configures virtual machines, and it deploys our game server to them when it needs to scale based on player demand. These are called fleets. When GameLift deploys virtual machines, it spreads them across multiple availability zones within a region, giving us automatic resilience. But we can also deploy fleets to multiple AWS regions, giving us a multi-region resilience. Like with our backend services, we can use Amazon Route 53 GeoDNS to detect where the player is located, and based on this, pass a player game session request to a GameLift queue in a region close to them. GameLift queues efficiently place new game sessions on any fleet in a group of fleets that can span multiple regions. It is able to do so either based on the lowest latency or priority that you define. If a failure were to happen that affected a region, we can use Route 53 to route all players to a good region, allowing players to continue playing while the issue is resolved at the cost of potentially higher latency for that period of time. So let's have a look at how we can quickly manage a multi-region game server setup with Amazon GameLift. So we're going to take a look at the Amazon GameLift console for a little bit here. We're going to look at how we can set up and configure a queue, and then we're going to test failing over in the event of a regional issue. And then we're going to see what that does to how GameLift actually places our game sessions for us. So just to start with, I'll introduce you to a few terms that GameLift are important to GameLift. First of all, are builds. Builds represent actually builds of your dedicated game server. And as you can see here on my account, I've got several different builds, some of which are different games, and or I might have different versions of my game also deployed here. And I can have many of them actually deployed to my account at any given time. Also important to note is that I'm currently running in the Oregon region, but I can store builds across various different regions too, should I need to. With GameLift, I actually need to integrate my build with the GameLift SDK, which supports both C# and C++. Next, I have here in my account 2 fleets. Well, actually, I have more than this. These are just the fleets that are deployed to Oregon. I actually have a copy of this particular fleet also deployed to the North Virginia region as well. So we'll see me using that in a queue in a second. But just to take a quick look at a fleet. A fleet is, as I said before, a collection of automatically scaled AWS infrastructure that GameLift deploys your server to and scales automatically up and down based on demand. And you can see here, this is an example that we've got running in an account at the moment, automatically handling player sessions and giving sessions to players when they request them. So let's take a quick look at the queues and how we can make use of those. Again, in my account, I've got several queues here, and actually on my dashboard for queues, I can see what my timeout is. This is how long we will wait for a player to find the session before we time that player out. And then I can also see how many destinations are in each of my queues. Some of them have 2, and some of them have 1 here in my demo. We're going to look at Aliens versus Cowboys queue, and we're going to see how this one's already configured. By clicking on that particular queue, I can look at a few things. First of all, I can look at the metrics for this queue. And if I scroll down, we can see here various different metrics about what makes up a queue and how it's running. In this case, I've got the queue depth automatically showing for me here. And this tells me how many players are waiting for a game session in the queue at any given time. So ideally, we want this to be as low a number as possible. And you can see occasionally in my demo account, I've got up to maybe 2. That's when loads got somewhat higher. But I can also see things like what the average wait time for players is, for example, or how many placements have actually been started over time. So you can see quite a few placements are constantly being pushed into my game server here. This has just got a kind of a little a script that's running constantly to generate load for my queue. I can also set things like latency policies, as I mentioned earlier, in my queue. And I have some example latency policies set here. While these do apply to this queue, I'm actually going to be bypassing these latency policies in this demo today because we're just going to be testing failover. But if I actually provide latency information from my clients and from my players to the queue, it will take those into account and use them as rules for finding the best fleet for our game session. And then finally, I have the destinations that are part of my queue. And really these are just Amazon resource numbers to point to the fleets. But we can see here that my highest priority destination is a queue in US East 1, which is North Virginia. And my second priority is one in US West 2, which is in Oregon. So we're going to test how our GameLift actually moves my game session, creates my game session based on these priorities. So let's take a quick look at that now. So I'm just going to come over to the my command line. And what I'm going to do is I'm going to test this by just running a couple of simple command line instructions into my account. So I'm a lazy person, so I'm just going to copy and paste some pre-canned commands into my console here. And this command is just really simply going to create a game session placement. And what that is, it's actually telling GameLift, please, for this group of players, actually create me a session and find them the best place to play based on the queue rules. Now, this isn't a particularly realistic example because actually what's happening is I'm not putting any players into this request, and I obviously would in the real world normally. And equally, I'm also not providing any latency information. So really what this is going to do is this is going to create an empty session for my players. But that's okay for this type of test. So if I run it now, what we'll see is GameLift will come back to me and tell me that, okay, I've accepted the request and that you've now got a status of pending. So we don't know any more about at this point as to where our placement currently is and where it's been put in our infrastructure and in what part of the globe. But hopefully by now, GameLift will have actually found a place to run this session. So I'm going to run another command to check this out. And I'm just going to describe the game session placement. And I'm going to use the placement ID that I defined up here just to find what the status of this particular placement is. And we can see that actually that's good. We've actually had it fulfilled. And we've got several pieces of information about this particular placement. But the ones we're interested in for this test are where did we get this session placement made? Well, we can see here it was US East 1. This is where the game session ID actually is. I can see it here. And it's gone to our North Virginia fleet. And that fleet ID is also kind of listed here. So we can check that against our queue and just make sure that, that's exactly where it got placed. Yep, US East 1 to that particular ID. So that's used our priorities and it's found us the session based on how we wanted to generally route players. Like I say, if it was latency information, we may have gone to the other one, depending on what our latency values are like. So let's now test a regional failure and let's simulate that. To do that, I can just edit my queue and I can go into my queue and I can modify the destinations that are available to GameLift when it needs to place the session. As you can see here, our US East 1 region is the priority, and I'm going to just simply remove it from the queue and leave us only with US West 2, our Oregon fleet. And that's what I'm going to do, literally just have that now in the queue. And we can see here I've now only got the one destination, and we're going to see how that impacts our placement. So I'm just going to clear the screen so we can see what we're doing. And I'm going to go and rerun these commands, and I'm just going to create a different placement ID. I'll just add another number onto the end of that, just so I've got a unique ID. So I'm going to run that again, and yeah, we've got GameLift telling us that we're just about to create this placement for the game session, so it's pending. And if I check in with that and see where we've placed it, hopefully it will have fulfilled by now, and it has. And looking at this information, you can now see that, yes, we continue to fulfill this session request, but now it's in US West 2, and it's using that other fleet that we've got defined, what was previously our second priority fleet. So even in the event that we completely lost our region and had a catastrophic failure, we were still able to actually place a session for a player into our other alternative region. And in the real world, where we had lots of load, we would probably be using both of those regions anyway. So GameLift in this case would have used the other region and then scaled up the servers within that region to meet the additional demand that's being driven to it. As I say, the downside here potentially for players is that if we have to route them to a region that's slightly further away, then latencies could go up. So you do need to bear that in mind with your overall global deployment and what you might do in various scenarios of failover. So the final responsibility that we had identified in our example is game content distribution. Getting our game content and updates to players as quickly as possible is key. Game content is getting harder all the time. It's getting larger all the time, and with 4K gaming becoming more mainstream, this is a continual upward trend. If player experience is slow for downloads or players have to wait for long periods of time, this can cause them frustration and possibly to abandon our game. So we need to make sure that our content distribution system is capable of scaling and handling spikes in player demand, and that it can get the content as close to as many players as possible to ensure fast downloads in a secure way. To meet these needs for our game, we can make use of Amazon Cloudfront to put our content much closer to the players. Amazon Cloudfront is a service that delivers your content through a worldwide network of data centers called edge locations. When a player requests content that you're serving with Cloudfront, the player is routed to the edge location that provides the lowest latency, so that content is delivered with the best possible performance. So how do game developers benefit from Cloudfront? Well, they use it as fast, scalable way to deliver game downloads. We routinely see them deliver multiple terabytes per second in peaks globally for game downloads particularly. Customers put their binaries or user-generated content or game analytic information for leaderboards, things like that, in Amazon S3, and then they use Cloudfront in front of that to get improved performance and also save on costs. Cloudfront benefits both static and dynamic content acceleration as well. And of course, we have security at the edge as well, which is a big benefit, especially as games are a target for DDoS attacks. And finally, we allow advanced customization for the requests and responses within Cloudfront too. So this map gives an idea of how Amazon Cloudfront is distributed around the world. There are currently 136 points of presence that span 62 cities and 29 countries. Making use of these for game downloads can help to reduce origin load, improve the speed of downloads for players, and give you access to pay-as-you-go pricing with no egress fees from within AWS. There's varying levels of resilience you can build into your game, audience, and budget. But by building a resilient infrastructure, you can deliver a great gaming experience for your players. Thanks for joining me today to learn how AWS enables you to build resilient games. Stick around for the next session on the Amazon Game Tech track and learn how to scale your game's core backend beyond viral levels. I will be sticking around following the sessions, so please reach out with any questions that you may have and we'll be happy to help answering them. Thank you very much.